Okay, we should be live. I think. So rusty at this. So many buttons to press. Uh, how's everybody going? How's everybody doing? It looks like an Australian thing. How's it going?
Great.
No. So who has fires in their neighborhood right now? Yeah.
I'm in middle
Yeah.
of
I don't.
Pennsylvania and our sky is getting smoky from all those fires. Like it's gone all the way across the country.
Yeah, you're on the East Coast
I'm in
now.
Western New York, and it's the same thing.
Yeah, and
Yep.
it's making it over to you now.
Yep.
Hmm.
We're starting to look like Tatooine.
Yeah.
That's how it was with us 2 weeks ago, and then it snowed. So,
They keep
Wow.
resetting, so they keep saying that we're gonna have like a storm come in and clear out the smoke, but it just is not. It is yeah, it's pretty nasty. Like I said, I was mentioning, so we have the scale that goes from 1 to 10, and so when it gets to above 7 or so, we only see bad pollution when there's forest fires, and the scale has been stuck at 10. So like I don't even know how far it goes. Does it go to 20? Like we're on the other side of this right now. So I
Yeah, I
really
think
do
the
hope the things cool down, things get wetter, and of course we're watching with horror Mount Wilson Observatory,
yeah.
which is going to be scary. So I
I think I saw last night it was within a couple hundred yards of one of the domes.
Oh, wow.
yeah, I they seem hopeful.
Yeah.
They seem hopeful, and you were mentioning that they've been prepared for this situation, Carolyn. That they've got a lot of protective gear up there.
With
But
that and a big cistern full of water, and they have a whole new system of fire suppression, water delivery for that, plus about 100 firefighters. So, yeah.
yeah,
Oh, and I guess they've been hitting it with the tankers really well,
that's
too.
right. I saw that too. So I wonder if like at some point they can just press a button and just release all the water from the big cistern and have it
Yeah.
just flow down the mountain. I don't know if that'll
Yeah, but
work.
if I were one of those tanker flyers, I wouldn't, you can't hit the observatories with that slurry because it would just
Yeah,
bomb the what out of it. But they want to get really close. So
yeah,
you'd have all these orange domes up there.
yeah. So it's like, did you save them if you've like dropped flame retardant on all of the
Yeah, yeah,
astronomical equipment? Yeah,
Well, come on, orange is the new trendy color now, right?
yeah.
yeah, yeah.
It's just a different kind of filter, maybe. I'm going to say hi to some people. I forgot to do this last week. Hello to Andy Cowley, Beth Johnson, Bill Smith, David Dunn, David Fairweather, DPI 209, Eric Knapp, Ian Farquharon, Johnny J, Larry Beckham, Larry King, Miguel Angel Romero, Naja Shiel, Neil Yu, Paranor, Arjone, Ron McCoy, Susan Hunter, and Zappan Zappan. Hey, everybody. Wow, Andy Kelly saying the Smokies now as far as Europe. And Susan Hunter's asking where the force field is. Isn't
Really.
that what the dome is? Like I've seen Star Wars, right? Those kinds of domes, isn't that where the shield? Aren't they shield generators? Yeah,
Yeah, that's one part of them.
yeah. But I know I've heard.
They're the hemispherical ones, or the shield generators on top.
Right. Yeah, I had
So,
heard that some amateur observatories got taken out in the mountains. So, but none of the actual big astronomical observatories yet. But still,
yeah, they got
yikes.
webcams for
Yeah,
Mount Wilson, right? Like you can
Yeah.
look at it, you can see the fires. Like
yeah,
it's right there.
yeah. Did you see the? I highly recommend following Kevin Gill's picture feed, and he posted a picture from a webcam that's on the top of a tower that's like 2,300 feet tall. It's like one of the tallest
Wow.
freestanding radio towers out there, and looking down, and it's just fire underneath it everywhere as
Yeah.
far as you can see. Oh, yeah, that's very bad. All right, let us get onto the show. There's Michael on my screen. All right, there's me. Do I remember how to do this? We did this last week. All right. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, September 16th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, I don't know, it's been a pretty quiet week for space news. I can't think of anything really big that we're going to talk about, but we're probably going to talk about Venus, I'm assuming. We'll talk about dark matter being more distorting than anyone thought, and diamond planets and a exoplanet found around a white dwarf. Joining me this week on my screen, we got Michael Roderick. Michael, welcome back.
Thank you. It's been a while.
It has been a while. Hope you had a relaxing, quarantined summer.
I survived. I'm still here.
I hope you had a survivable summer. Ready for a survivable fall until we all get our vaccinations, which I hear will be in late 2021, maybe, after they've sort of supplied everybody who needs them before us. So yeah. All right. We've got Carolyn Collins-Peterson. Carolyn, welcome back.
Hey there. Thank you. It's been a while.
It has been a while. I get the same number of months as everybody else.
Oh, that's true. Mid-June or
Mid-June.
July. When was it?
I'm not
Yeah.
sure. Time has no meaning. It was tomorrow
That's
and
true.
yesterday and eternity.
And I join you in the smoke-filled room here, actually.
Yeah. Oh. We got Brian Coberline. Brian.
Hi, and good to be back after the summer break. So.
Yeah. I hope you also had a mildly relaxing, survivable summer break.
Considering the alternative, it's just been pretty uneventful.
Yeah, exactly. All right. So before we get into this week's interview, I just want to give a huge shout out and a thank you to our good friends at the Weekly Space Hangout crew. These are our friends. These are our fans. They are the executive producers of the show. I am looking at the future guests of the Weekly Space Hangout, and they are going to blow your mind. And yet this was completely organized by the executive producers at the Weekly Space Hangout crew. So if you want to be a member of this great group, just go to wshcrew.space. You can get your own business card so that you can be an executive producer of the show. Invite whatever guests you want. Come on, Elon Musk. And just join that community. So wshcrew.space. All right, let's get on to this week's guest. We've got Dr. Merav Ofer. Merav, welcome to the Weekly Space Hangout.
Thank you for inviting me.
All right, so who are you? What do you do?
I do very boring things.
I disagree with you.
Yeah.
So where are you located? And
So I'm in Boston, in Newton, suburb of Boston, and I'm a professor at Boston University in the astronomy department. And my department is a little unusual because it has a lot of space physicists, and I'm one of them. I dabble in both. So
right.
But
And you, I think your work came to our radar fairly recently with a cool new graphic of the solar system, and I'm going to find this and show it off because it's so weird. It kind of looks like a croissant, I guess. Is that the one? Yeah. All right.
yes,
Yeah.
if
So
you take, I like croissants.
Yeah. Or I don't know, like a stomach. I'm not trying to sure. So that is not the solar system. Like I remember the solar system to have like a sun in the middle and then a bunch of little lines that go around, a bunch of little circles and planets going around that.
Mm-hmm.
And this picture does not seem to indicate that. So can you please help us understand what it is that we're looking at?
So what you guys in this croissant yellow shape, you're seeing the outer part of the solar system. So the planets are still there, sun is there, but they're still orbiting the same way, way close to the sun.
So where in this sort of yellow blob is the sun? Is it in the middle?
It's in the center.
Okay.
It's in the middle.
Okay.
And you can think that maybe halfway between the center and the edge is the last planet.
Okay.
And I'm going to say Pluto, but anyway,
It's all right. It's all right.
Anyway,
we won't start a war here
don't
on.
start. Yeah. Anyway, so the last object rotating, and then that yellow surface is our, I like to call it bubble or cocoon. It's our home in the galaxy.
So how did you like produce this image? What is the underlying data that helped you get there?
So this is from a computer simulation. And I use a lot of inputs from spacecrafts. And I was also trying to predict other data as well. So what you're seeing there, it's the outer, it's from a computer model, and that yellow surface is the outer edges of this bubble. So you can think anything outside is interstellar medium. And anything inside is what we will say our solar system. So solar system, it's not just the sun and the planets, but it's the space filled by the wind from the sun, the solar wind.
Right. And I know that whenever we talk about how big is the solar system, you sort of have to define your terms. Like, are you talking about the orbit to the last planet, of which we won't say which one that is? Are you talking about out to the Oort cloud? Are you talking about the Kuiper belt? Are you talking about the heliosphere? Are you talking about the helioshock? Where? So in this case, which of those terms does
I haven't heard the term helioshock. I like that one.
Oh, okay.
Bioshock.
Yeah,
Public, yeah.
Yeah, so which one of those was that in the
So
picture?
that one is definition here is the surface where you don't have any more particles
Right.
that emanate from the sun. So it's the solar wind.
Right.
So it's that surface. The technical word is heliopause.
The heliopause.
Is where the I like when I teach my students. I say, you think about like water, oil mixing a little bit. In when you have magnetic fields, they don't like to mix.
Right.
So you really have a boundary. So this is the boundary, the heliopause.
And the heliopause, this is where the impact of the interstellar medium that we're passing through, the combined solar wind of all of the other stars in our region, are stopped by the sun. Like, this is the point where the sun, where the two come together. It's funny, we have here on Vancouver Island, we have a ferry boat that we take from Vancouver Island to Vancouver, and there is the outflow of the Fraser River passes out into the Georgia Strait, and it creates this brown sort of sedimenty coloration in the river, in the ocean. And then you take the boat and you go right across it. It's like a line, like a perfect line in the water. And I always sort of imagine it being that this is where the heliopause of the Fraser River is reaching the interstellar medium of the Pacific Ocean.
But it's not really such a boundary. I like when I describe this boundary to say it's not like your walls of your house that you're inside or you're outside. We saw one of the questions that this center I'm running from NASA, we have, hopefully we'll get funded for more, 5 years, but we have 2 years to start gearing this center, and it's called SHIELD, because we're trying to understand these properties of this wall exactly, the heliopause. Is it a wall, or maybe it's more porous? So when you're saying that there is really a separation, we had 2 spacecraft, Voyager 1 and 2, that crossed that boundary, and they saw very different data. In case of Voyager 1, the particles from the sun escaped before we got there. And so it's almost like somebody opened the window and the wind escaped and then closed and opened again, and then we left. So it's, I'm not sure how much is a boundary. We're still trying to figure out.
Right,
It is kind of a boundary, but it's not totally closed.
And we only have 2 data points to be able to really take a look at so far.
Right.
We need to wait for New Horizons to actually complete the journey and record some data as well to get that third data point.
We actually, New Horizon probably won't have enough fuel to get there. They will get to much later than that, much earlier than that. Maybe 90 a year. They won't get to that boundary and had fuel, but there are, talks about something called interstellar probe to try to launch and get there again.
So like send a brand new spacecraft to try to do that.
Right, with modern instrumentation. These two
Right.
spacecraft were, a technology from the 70s. So they're trying to
It'd be amazing. Yeah.
revisit that. That would be great. Yeah,
But it's a long journey.
it's a long journey.
Yeah.
Right.
So you have to be very patient.
Yeah, we have other ways to look at this interaction with energetic neutral atoms, with IBEX and Cassini, and now there will be the next big mission in my field that will be launched 2024. It's called IMAP,
Right.
and it will be, taking, it's almost a tomography of that region from near Earth. But it's not the same that sending a probe that is going right there and
Yeah.
collecting. So it's different.
So I guess what are the factors that will change the shape of it? Because like it has this weird little tail at the end. And I know that, in fact, we saw fairly recently that scientists know that, in fact, we seem to be flying through the debris of an ancient supernovae, that we're going through something called the local fluff as well. So what are some of the factors that will define the size and shape of it?
Well, it has to do, we discover this new shape that is not, the traditional one that is a comet-like comet tail that extends for many, many astronomical units instead of these two horns of a sun. The funneling of the plasma by these two horns is set by the magnetic field of the sun. So this is one factor. As the sun changes, there is a cycle from the sun. So and actually another interesting caveat, probably many stars have sun-like shapes like that because they have magnetic fields like the sun. So one factor that is interesting, they all will funnel plasmas like that. And it's always the interplay between the magnetic field of the star and the pressure from outside. So you mentioned local fluff. As we leave the local fluff go, we actually don't know where we are exactly in the interstellar medium, but as we go to a different region outside the heliosphere, we will get a different pressure from outside. So then different magnetic fields, so the shape might change.
Right. And is there, in order to be able to see the shape of the heliopause around the solar system, we had to pierce it with a couple of spacecraft. And you mentioned some ways to be able to detect it with some other instruments as well. Is there anything that could give us a very comprehensive mapping of it through some kind of interaction from here on Earth? Something more like, say, the cosmic microwave background radiation, but looking at around the solar system?
So we are trying to figure out, maybe there's more creative ways, but the one that we're trying is the medium in the interstellar medium is not completely ionized, it's partially neutral. So we have atoms streaming inside, and they go through a certain process called charge exchange, and they create maps for us. Like the cosmic microwave background, you got a map in 3D, and you are at Earth looking up, and you see a map of this emission. And that emission is called energetic neutral atoms, and you can have the shape of the heliosphere or the heliopause mapped into this energetic neutral atoms maps. We have right now, like I said, IBEX mission taking pictures, but the energy range that IBEX take, it's really, you cannot probe much farther in the tail. So it's hard for you to distinguish between a sun shape or something else. But I think what is exciting in 2024, when IMAP come up, IMAP is sensitive to high energies. And this means we will be able, it's almost like a fog. You get the better glasses that you can really see deep. We will be able to really see stuff coming from the back end, the tail of the heliosphere. And I think this question of the shape, the croissant shape, I think it's going to appear in the maps.
Oh, wow. Oh, that sounds great. Now we are, again, we always, as the hunt for exoplanets and for other stars continues, we're starting to see really interesting red dwarf, M dwarf worlds with M dwarf stars with planets around them. But we know that these M dwarfs have really awful solar flares and quite energetic activity on them. Would there be a way to be able to perceive the shapes of the heliopauses around other stars?
Absolutely. This is my next big thing that I would like to pursue in my research, because all these M dwarfs are very active, and we're always thinking about habitability. If you put a planet near a very active star, what kind of like bombs that star is going to send to the planet. But we forget that beside the fact that it's close to an active star, even for the sun, when the sun goes quiet, it's shielding the whole system of planets from particles coming from the galaxy. We call that galactic cosmic rays. Those galactic cosmic rays affect the evolution of life. So those M dwarfs almost certainly are immersed within an M star astrosphere, the equivalent of a heliosphere. And because those M dwarfs have winds, they move through the interstellar medium, they will have a bubble. And what is interesting too, they have a magnetic field. Whether the shape of these M dwarf astrospheres will be a croissant, comet-like, a bubble, we don't know. It's very hard to detect those. But we know that they will shield those planets from galactic cosmic rays. So
Right.
it's a really baby area. We're
Yeah.
just starting to think about it, because until a couple of years ago in my field, you was said, "Oh, we know the heliosphere," and then suddenly we're saying, "No, it's called sun-like." So
Yeah. I mean, I just sort of imagine this perfect balance. On the one hand, you've got these red dwarfs that are blasting out awful solar flares that are going to scour their planets of life, but also generate very protective bubbles that will help protect them from galactic cosmic
it's
radiation.
very possible.
Yeah.
Because the magnetic field is strong. It really will depend. But because it's so strong, it probably does, like you said, a very protective bubble.
Right. And so
Yeah.
could you, in addition, like already we're saying, we're looking at planetary systems that have planets that are in the habitable zone, but maybe we need to have a habitable magnetosphere, heliosphere as well to contribute
Right.
to that factor as well. And what would
Right.
a habitable heliosphere look like?
It's a very good point. Like when I just was applying for a big fellowship, and I say I want to study other astrospheres.
Yeah.
The only habitable known is our heliosphere.
Right.
And right now we discover it's completely different than we thought. So we have at least one data point in our universe
Yeah.
that the habitable astrosphere look like a croissant.
Yeah.
And it's actually what the other interesting fact, that now that we left the bubble with the Voyager spacecraft, we know how much this bubble shield,
Yeah.
and it shields 75%.
Wow.
It's a whole lot of shielding
So
of galactic
the
cosmic rays
heliosphere
around.
is keeping us safe.
It does.
Yeah.
In 75 of that 1 GeV that is important for life, we are. And it's shielding right now. It's one data point in time. How it was in the past or how
Yes.
it will be in the future might change.
And I wonder as well if being able to see the heliosphere around another star, it's more of an average as opposed to just seeing a snap. Oh, we just saw a flare off that star. It's a bad star. You're seeing more of an average of how it looks over a long period of time and as it changes because
Right. You will need to look at these astrospheres over a long period of time
Yeah.
and say, is it protecting?
Right.
And it's much more stable than a flare. A flare
Yeah.
goes off. But that astrosphere It depends on average on what's coming in the outside and average what the wind from the star. So in average would be a certain shape and certain shielding properties.
Oh, absolutely fascinating to think about. Thank you so much for
Thank
taking the
you
time to
for
chat with
having
us
me.
today. Where can people find out more if they want to watch the this next paper? This sounds great.
You know what I suggest, or going to my webpage, so you can just Google Merav Ofer and email me. I am happy to answer any questions.
Wonderful.
Another, if you want to go to the shield, let me just, let's see if I can share a screen and show you. I think you have to enable me.
Oh, okay.
But either,
Let's see. There. Okay, you should be able to share.
okay, so really quick, though, if you want, you can go, if you just Google Shield Drive Science Center,
Yep.
it's shown here, sites.bu.edu. Or you can just go, if you go to my website, there is a link.
Perfect.
You just
Yeah,
do
we're gonna have a
Merav
link.
Ofer
We'll have a
BU.
link in the show notes as well.
Great. And then you can see there's outreach, there is lots of interesting, there is research when you can learn
Perfect.
what's happening. Okay, great.
Wonderful. Great. Well, thank you so much for taking the time to chat with us today, and good luck with your research.
Thank you. Thank you for having me.
All right, let's move on to the next segment. I guess we should probably talk about anything but Venus. We'll get to Venus in a second. Brian, you're on my screen right now. What do we got?
So this is some new stuff out about dark matter, which, as we all know, is definitely real. We just can't find it. The problem with dark matter is that we've searched for, direct particles in various detectors and have found nada. But we see evidence of it in the cosmos and the way galaxies cluster. We see how light is gravitationally deflected around galaxies and galaxy clusters, which shows that there's more mass there than the visible mass. So we've got a lot of evidence to support dark matter. And what's starting to happen now is that you're getting more and more accurate observations, particularly of gravitational lensing. And we're starting to find some interesting properties of dark matter. And so this most recent study was looking at a large I think 3 large superclusters. And basically a supercluster is a cluster of galaxy clusters. So there's a whole bunch of galaxies in one kind of gravitational region. And we know that dark matter is basically in kind of halos around galaxies. But when you have kind of a large, dense cluster, we've generally thought by what we'd observed is that the dark matter kind of spreads throughout that region, that basically it doesn't clump in the way that galaxies clump. And so they did this observation of these superclusters, and what they found was, okay, around the supercluster, you're getting this gravitational lensing, but around individual galaxies within the supercluster, you're getting hard lensing. You're getting lensing around individual galaxies within a cluster. Mm-hmm. And that is kind of surprising, because what it says is that the rate that you're getting those lensing means that you got dark matter not just clustered within the galaxies, but actually clumped around individual galaxies in the cluster. So that lensing is stronger than we expect.
So,
and that, go ahead.
Well, I just I don't know, what's the,
so this is one of those things.
I mean, I guess. Yeah, go ahead.
This is one of those things about dark matter is it doesn't interact strongly with regular matter. The bullet cluster is a thing where you see the cluster matter, but then you see the dark matter, in a different spot. It's not interacting in the same way. So if it doesn't interact strongly with matter, what we don't know is how strongly does it interact with itself. And so there are different models. Some models will say that it doesn't interact very much with itself, so it's kind of blurry. Mm-hmm. And others say that it could interact with itself. And in fact, some people have looked for light coming off, like gamma rays coming off from colliding dark matter particles. So what this is saying is that this matter is clumping more densely than we thought. It is clustered around galaxies in these superclusters, more dense than we thought. And when we talk about dark matter, we typically talk about cold dark matter. Like neutrinos are dark matter. They don't interact strongly with
Right.
light, but they're very hot. The particles move at nearly the speed of light, so it can't clump into things. So that clustering of galaxies we see, that clustering of dark matter, means that dark matter is cold. But if we're getting really tight clumps, that means in some sense it's colder than we thought. It's clumping more than we thought.
But it shouldn't be able to clump.
Well, that looks at different models. That would imply that somehow it's interacting in such a way to cool itself down, to clump more.
Right.
Regular matter clumps because it collides and stops
Right.
when it collides.
Right.
And so that motion is impeded. This implies that the motion of dark matter interacting with dark matter is also impeded. So that helps kind of filter through the different dark matter models.
But I almost feel like we're having like a return to our conversation that we had last season when we were puzzling out dark energy, that you've got dark matter behaving differently from dark matter.
Yes. So I mean, one of the solutions is you can have different types of dark matter. We think of dark matter
different types of dark matter.
Right? We think of one type of dark matter. So dark matter is one particle. It's like the Higgs boson. Once we find it, we're done, right? Well, there could be different dark matter particles. There could be different types of dark matter, and some of it may clump densely and some of it may not.
And so I'm sort of imagining, like you did another article actually last week about what dark matter would look like if we could see it, and these really great simulations that showed the dark matter but in a more visible look. So would we see, like, if now we might see like different colors? Some of it is more diffuse and much more spread apart, and others is clumping together and forming very focused lenses. I mean, someone in the chat is mentioning compound lensing. Like, is it the equivalent of interfering waves or something?
It's in this case they're just looking at the strength of the lensing, and basically the amount of lensing that you get, the scale of lensing that you get, depends upon how dense the mass is. So a really dense clump of matter is going to lens really strongly, and a diffuse one is going to lens less. So what this is showing is that, unless some dark matter does some weird thing with light, dark matter is clumping more tightly around these galaxies than we thought.
Right. And because it doesn't interact with itself, it doesn't seem to have a cross-section, it shouldn't be bonking into each other and colliding and piling up in the way that it seems to be doing. And
yes.
And so sometimes dark matter behaves quite nicely as something that can't pile up, and now it appears to be behaving like something that can pile up.
Right. But I will say that, just like we talked about with the dark energy stuff, we're getting more data. And that's the real thing, is that we're being able to observationally define dark matter more accurately. And then the theorists can figure out what's going on.
Yeah.
So there was some news story I heard, I think in June or maybe earlier, again, time blends together in 2020, but that there was a potential detection in one of the xenon dark matter experiments. Has anything like come of that? Like, I know it's like, yeah, it's a detection, but probably not.
I haven't read the analysis on it. I think it's one of those things where it's sometimes these things happen and then you have to really look at the data, and then if it pans out, you'll definitely hear about it everywhere because it'll be the next Nobel Prize.
Right.
If it doesn't pan out, then you may not hear about it. It'll be buried in journal number 42 of
so
classical quantum gravity or something.
Larry Beckham is mentioning in the chat, well, we have many different types of visible matter, at least 110 to 120 different types of atoms. So, I mean, it would seem like it would be weird if there was one type of dark matter. It almost seems like of course it's going to be more complicated than we expect. And so what is the way to tease more information? Better gravitational lensing experiments?
better gravitational wave experiments, more detection attempts, even some particle physics. Particle physics has ruled out some of the dark matter models because we now have enough accurate measurement of things like supersymmetry that we know they can't be like the standard supersymmetric particles.
Right.
So there are lots of avenues to pursue. I think in some sense we're really just getting started with this.
That's amazing. Awesome. Carolyn, what have you got for us?
Unmuting my mic, actually.
Okay.
Sorry.
Now that you can talk.
Yeah, so I'm currently working on a script about exoplanets. So I've been digging around in the exoplanet literature, and the story that caught my attention the day before the big Venus announcement, which I guess we're going to get to, was about, it had a really catchy headline. It was about diamond planets. And these are like supposed to be carbon-rich planets that may exist around other stars. And granted, I don't think they haven't found any yet, but a group of scientists have been trying to figure out what the possibilities are for planets that could form in these carbon-rich protostellar nebulae. So like our nebula had, a different mix of materials in it. These would have a little bit more carbon instead of a little bit more silicon. And they decided to mimic the interior of a carbide planet, which is what this would be. It's carbon and silicon and oxygen, sort of carbon in a silicate matrix. And they took a bunch of silicon carbide, which is like that compound, and they decided it's quite plentiful in star-forming regions, and they decided to subject it to really high pressure. So they put it inside of this instrument called a diamond anvil cell. And that's a material science instrument that geologists and other people use, and has got 2 diamond pressure plates. And you push this stuff in between the pressure plates, and you take it up to pressures of somewhere, they didn't say exactly how much, but somewhere between 100 to 700 gigapascals, which is really high.
Yeah.
They compressed all of this, and they came up with, then they shot it with a laser, and they basically could figure out that they could turn this material into a world that would be made out of silicon, diamonds and silica. So that's what they did. They simulated these conditions. And basically they came up with this planet that is a diamond with a silicate structure sort of lacing through it, which makes sense if you understand how the stars and planets formed. So that was their experiment. And then the next question that sort of came up was, well, would there be life on could you support life on these planets? Because we're all about searching for life right now, right?
Right.
Can't get away from that.
That world sounds awful.
And so, you have this star that sort of formed with this bulk composition of carbon in it, and it's got these diamonds. And of course, I immediately thought of Arthur C. Clarke and the diamonds at the center of Jupiter, which is sort of a whole different regime there. And basically saying if these conditions were right, you could form these planets, but could you have life on them? And the question is, it's a good one. I mean, short of diamond merchants going out there and looking for this thing and trying to cut it up. Basically, up until the phosphine announcement that we're going to hear about, I was saying, and people were saying, well, there's probably not a chance there's going to be life elsewhere. We haven't found it yet. But life is very tenacious, and it doesn't have to live on a planet just like our planet. We're still looking at Mars. We're looking at Venus. We could look at this carbon planet. But there's a few problems with a carbon planet, and that would be that, first of all, it wouldn't have that much geology to it. It wouldn't have that much like plate tectonics, the kinds of things that sort of formed, that spurred on the formation of life on this planet.
Right.
It would have water. Most likely there'd be water in there, but it wouldn't have the properties, the plate tectonics and the geologic properties that you'd want to see to form life. And then the other issue would be, what kind of magnetic field would this world have? Would it, because we kind of depend on our magnetic field to protect us from all kinds of things now. You also wouldn't be able to form much of an atmosphere on a world like this. So sort of the answer to their question was, yes, you could form these planets, but you really probably couldn't have life on them. It doesn't mean there isn't a carbon-rich planet out there teeming with life. But if it is, we don't know what it looks like.
Right. I mean, no shortage of carbon, at least.
Yeah.
So that one element is in spades. But then it's just, you've got carbon to breathe, carbon to swim around in, carbon, and then, of course, diamonds. Everything's made of diamonds.
Yeah, and I'm sitting here thinking, it'd probably be a great investment opportunity in about 1 million years if anybody wants to get out there and find it. But but could you land people on there to work on something like that? That's sort of thinking far out in the future in the Arthur C. Clarke realm of, would we be landing people on this? We're probably not going to be finding carbon microbes or carbon eating microbes or whatever. Although, I mean, life is strange. Life eats methane, life puts out methane. It eats all kinds of stuff. So, but right now, looking at the geology of the world and sort of the other structures that you would need to have to support life, not so much. But yes, we probably could form them, especially if you've got these stars forming in a carbon-rich environment anyway.
Yeah, I mean, it's possible that we just posted a story on Universe Today about life maybe being inside stars. So, who knows?
Yeah.
Where life could be. That's awesome. All right, I've made everybody wait long enough. Michael, give us the big news.
We found aliens.
We found aliens. We did it.
I knew it.
So it's a pretty unusual discovery, the discovery of phosphine in the atmosphere of Venus. And that by itself doesn't sound too remarkable. But the special thing about phosphine is that we do not know of a way to generate phosphine with our current understanding of Venus's atmosphere and its geology. So the way that we find these things, when you try to look for aliens, when you try to look for life, it's usually a diagnosis of exclusion, where you can't explain this through any other method that we currently know. So for Venus, we took a spectra of it, and normally maybe it should have just been a flat line, but when we looked at it, there was a little dip in that spectrum. And that dip is due to phosphine, which is absorbing some of the lights in the millimeter regime in Venus's atmosphere. So on Earth, you can produce phosphine in two ways, either industrially or biologically. And this occurs when microbes can eat something, they can process material. We were talking before the show about how they found phosphine in fecal matter of penguins.
Right, penguin poop.
And so, penguin poop. So microbes that are present in some kind of anaerobic environment where there isn't oxygen can produce phosphine. You can produce it in Jupiter and Saturn. We see it in their atmospheres, but Jupiter and Saturn are much hotter.
Right.
Even than Venus.
Well, and they have a hydrogen-rich environment, and they're starved for oxygen. They're all hydrogen and helium with only a tiny little bit, so makes sense. But here on Earth, plenty of oxygen. Venus, plenty of oxygen, just locked up with carbon. But carbon would be glad to, or the hydrogen would be glad to jump and connect up with the oxygen from the carbon dioxide. Like that's so there's so much oxygen at Venus ready to gather up all of that phosphine that's created.
Yeah. So like right now it's, the paper, they take great pains to say we have not discovered life. We discovered something unusual. We don't understand the chemistry of it, and we need to further analyze Venus to get a better idea of what's going on.
One of the things that I found quite fascinating about this was how long they sat on these results. They did these original observations 3 years ago, and they knew that they had potentially discovered phosphine. And then they did more observations using ALMA, which is like one of the most powerful telescopes in the world, and found an even better signal of phosphine. But still took 3 years to let us know what they had discovered. Although I was mentioning this before the show, the signs were all there. There was a lot of interesting phosphine news that was coming out in the months leading up to this big announcement. How do you think, how has this been received by the scientific community? Because we've heard life on planet before, life on Mars.
I think people are reacting appropriately, and they are, no astronomer is out there claiming that we have discovered alien life. This is unusual. This could be a biosignature, but we need to approach this with caution. And so I I'm happy with the reaction, even from the press. I'm actually pretty excited that even, the press hasn't really jumped on it saying that we discovered alien life. It's been pretty subdued, appropriate reactions to this discovery. And so, of course, the next thing you want to do is you want to make follow-up observations for this. So, you found phosphine, you found one absorption line of phosphine. There are multiple other lines of phosphine that exist. So one of the next steps to do, if you can, is to try to do more observations of these other lines where we think you can find phosphine. The trouble is that if you want to do this with ALMA, you need like 3 days of ALMA time, and that is hard to get.
They'll
Or you
get
can
it.
try to do it with, yeah,
They'll get it.
probably, right?
Yeah.
Like if you're gonna,
Yeah.
yeah.
That's all this
And the other
was.
option
This was just like a really fancy proposal for telescope time. Was to say, can we use your telescope now?
It's kind of the best case scenario. You get this somewhat ambiguous discovery, like we need more funding, we need more money, we need more telescope time, and you kind of got yourself a career for the next few years. Yeah, and then the other thing I was gonna say is infrared. You can try to look for this in infrared. James Webb can maybe look for it, but the trouble you run into there is that there's gonna be a bunch of carbon dioxide lines right where phosphine should be. So it's kind of a challenge.
Also, James Webb would have to look out through a Northrop Grumman manufacturing facility here on Earth. So, yes, because
every time you mention James Webb, it
just keeps getting pushed back. Yeah. So it's only so well it can see from a clean room in California. So you talked about sort of follow-on observations. What about spacecraft?
There are currently no spacecraft I know of that are going directly to, penetrate the surface of Venus.
Right.
There is like Bepi Colombo, which is going to visit Venus pretty soon. It's doing a flyby, I believe.
Yeah, you need to get a gravitational slingshot.
Yeah, and then it's going to do another one in I think a year from now. So I think the observing program right now is pretty locked in, so they may not be able to adjust it to try to look for this stuff. But in a year, the quote I heard was, if we are very, very lucky, we can find evidence of phosphine now. And a year from now, if we are very lucky, we can find evidence for phosphine. So is an instrument sensitive enough to discover it? Not entirely sure.
So Unc Willie is mentioning in the chat that Rocket Lab has a planned Venus mission 2023. There actually are a couple of other missions. NASA has the Da Vinci Plus mission, which would drop a atmospheric probe down through the atmosphere, and some other more interesting, elaborate ones. The Indian Space Agency is planning I think a balloon mission to Venus as well, and the Russians have their next Venera program. I think is going to have a U.S. built temperature or atmospheric probe attached to it as well. So there were all of these missions that were in the works, but they were all slow burn. And now suddenly we see all this encouragement to maybe make this happen more quickly. So if it is life, how? What could be going on? What could be producing it?
Microbe poop, right? That's got to be...
You can't just say microbes. You can't just hand wave and say microbes, man. It's like microbes. They're like everywhere. Can't get rid of them.
Yeah, I mean, that's a really great question that I don't have a good answer for, of how life on Venus can survive and produce this signature. It's so different from everything that we know on Earth. It's so toxic to life on Earth that this has to be some kind of really new extreme microbe that is able to do this. I personally I'm puzzled by it.
What about something in the atmosphere?
Well, we know that at about the 50-kilometer altitude range, the temperature and pressure on Venus are similar to what we have on Earth. So down at the surface, it's 475 degrees centigrade and 90 atmospheric pressures. But once you're up about 50 kilometers, then you're looking at fairly reasonable 1 pressure, room temperature levels. Now you still have clouds of sulfuric acid, which are far more acidic than anything that we have where bacteria can survive here on Earth. But those droplets do have water dissolved in them at about 15%. So in theory, I was actually talking with everybody about this before the show as well, that Sarah Seeger who's one of the people who worked on this research, and we've had her on the show before. She had published a paper a month ago about a possible mechanism for how life could be surviving on Venus. And she was talking about that the microbes are essentially hitching a ride on water droplets. And the water droplets or liquid droplets, they're mostly sulfuric acid, but they also have water inside them. And they pick up more and more liquid as they go higher and higher in the cloud tops. And eventually they get too heavy and they rain down. And in theory, the microbes can maybe hitch a ride, quickly do their life thing, and then throw out spores into the atmosphere, which can then rain down and then get caught in this atmospheric haze at around the 30-kilometer level. And then they'll desiccate and they'll just wait until one of these droplets picks them up and carries them up. And so you've got these bacteria living their entire lives as they rise up through the atmosphere, as the droplets get bigger and bigger and bigger, hurrying to be able to release more spores, and then the droplet falls back down and rains down as sulfuric acid on the surface of Venus. So it's interesting, the timing that this paper came out a month ago, and now suddenly we see this big announcement. In fact, there's a ton of really interesting phosphine papers that, if you look back over the last couple of months, have come out. Brian, what do you think about
another paper?
Oh, go ahead.
I was going to say there's another paper that's titled "Phosphine as a Biosignature Gas in Exoplanet Atmospheres" that came out this year as well. So
yes.
Phosphine has definitely been on the mind.
Yeah. So Brian, what do you think about phosphine as a biosignature?
It's been discussed as a biosignature before. It's one of the more odd ones. I think what's interesting about this one, and kind of the surprising thing, is that it's a potential bioindicator on Venus, but in order to do that, it has to be very unlike terrestrial life. And we've talked about things like methane rising on Mars or something. We're really kind of imagining something that's very similar to terrestrial life, possibly even cross-seeded. There are places on Mars where we could have the right type of bacteria, the right type of living forms that could survive.
Yeah.
We could intentionally put life on Mars, because there are places where terrestrial life can survive.
And there's terrestrial life that's ready to, cyanobacteria. You just drop it on Mars and it's ready to go.
It's ready to go.
Yeah.
So that type of thing, when we look at something like Mars, we're looking at life very similar to Earth. Venus, there really isn't life anywhere that we know on Earth that we could seed into Venus, even its atmosphere, and really have a chance of it surviving. So if this is truly evidence of life, then it is truly an alien form of life. It's anaerobic. It has to deal with things like sulfuric acid. It has to deal with an entirely different environment that we have on Earth. Probably the only thing that's comparable would be something like Titan, where you'd have some type of methane organism. So that type of exotica, I wouldn't even call them extremophiles. That kind of exotica of life is kind of exciting. I mean, we definitely want to send probes that way. We definitely want to find out more.
Yeah, I feel bad for suggesting that we push Venus into the sun all these years. Now it's suddenly interesting. So I guess, could it be related to us? Michael. Michael, go ahead. Do you think it could be related to us?
I just, one of the things I want to mention is there's this term of lithopanspermia, which is my favorite term in astronomy, where you have a rock that collides with another planet. It shoots out rock from that planet. That rock gets flung into space, and then it lands on another planet, like on Earth. and then life transfers that way. So that just came to mind when he said that, and I just had to share that.
Yeah.
Well, actually, following that up, I mean, I'd seen questions and discussion about whether or not it was brought there by any of the spacecraft.
I mean, maybe, but I mean, to be to the point where you can see a recognizable signal across an entire planet seems highly unlikely that it got going. Like, life finds a way, but that's like really finding a way.
Yeah.
50 years.
50 years, yeah.
Yeah.
I guess so. Brian, what do you think you'll see? What do you think we will see happen next to make more headway on this discovery?
Well, you're definitely going to see more optical surveys of Venus, specifically looking at not only this biosignature, but other possible ones. The fact that you know that it's anaerobic, there are other molecules that you could look for potentially. So you're going to see a lot of proposals, to say, I need ALMA radio time in order to figure out these things.
3 days of ALMA radio time.
I need 3 days.
Yeah. Step aside, planet hunters. Yeah, we need this telescope. Yeah.
But I think one of the things it really does is that, the Venus, in terms of planetary exploration, has somewhat been the unwanted stepchild. And Venus is now kind of at the top priority for a lot of ideas. The fact that we're finding potential biosignatures means that we probably should look at some serious probes, not just the ones that are on the table, but much more sophisticated ones looking for life. And I don't think that's really been taken seriously. The idea that we need to have, like we've done for Mars, we're going to try and look specifically for life, go to Venus, go to that atmosphere range that's temperate, and actually look specifically for life, or indicators of that. That's going to be a game changer. That I think you're going to see in the next 20 years, plans to do that.
Yeah, that's amazing. So, I mean, I think that this will definitely not be the last. This is the beginning of a fairly intensive process. I find it so fortunate that this proposed biosignature, phosphine, has been discovered so close to home so that you can actually do these tests. You can say, is it really a biosignature? How does it behave when you examine it more closely? When you send a spacecraft? I don't think anyone was ever expecting that this biosignature would actually be so relatively easy to study. If we discovered phosphine in some other star system, in some other planet, really the search would end there. You go like, yep, we found phosphine, and that's and there's nothing else we can do about that. But in the case of Venus, we can send a spacecraft. We can examine the atmosphere directly. It's a whole different world. Fascinating. All right. Well, we've reached the end of our show. Carolyn, you're on my screen. Tell me what you're working on and where people can find out more.
Well, you can find me at thespacewriter.com. That's where I have my webpage, and I'm at Spacewriter on Twitter. And right now I'm writing a script about exoplanets, and that's sort of keeping all of my attention focused.
Fantastic. Brian?
You can find me on Universe Today because I post there. You can also find me on my website, which is briankoberlein.com. You can even sign up for a newsletter that'll start in October. So come on down and see that. I'm also on Twitter at Brian Koberlein.
Awesome. Michael?
I'm on Twitter at Michael Roderick. I mostly post stories about our Astronomy on Tap events, which are starting up now again once a month. Our next one is coming up September 28th. So we're going to have Corey Gray, who I believe is a Weekly Space Hangout veteran. I think he came on a year or two ago. And Evan Sneed. So we're going to be talking about biosignatures, about translating the LIGO detection to Blackfoot language. And I also post photos of my foster dogs, and so those are cute too. So
is this going to be a virtual Astronomy on Tap? Does everyone?
Yep, everything is live streamed now, so it's all on. Yeah, we do show you how to make an Astro themed cocktail beforehand.
Oh, good.
So that'll get your on tap.
Perfect. There. Yeah, that's awesome. All right, and if it seemed like I knew a lot about the Venus announcement, that's because I did a video on it, and we should be releasing it in a couple of hours tonight, so stay tuned on my YouTube channel. The Open Space is back. I did the new episode this Monday, and we're going to be doing we're back every week with more open space QAs and other shows across on the YouTube channel. Lots of good stuff on Universe Today. Sign up for my weekly newsletter. There's lots of, we're back from hiatus, hitting it hard. So I hope you all can get caught up on all the space news. All right, I'm gonna put everybody on the screen. Thank you, everybody, for watching this week. Of course, we really appreciate you joining us here, taking the time to watch. Thanks to all the moderators. Of course, Nancy Graziano, who wasn't able to actually watch the show, but she organized it behind the scenes. So thank you as well. And we will see all of you next week. And some of these people in weeks in the future. Thanks, everybody.
Bye.
Thanks. Bye.